to our next speaker, Raphaele. Professor Raphaele Clement joined the UCSB Materials Department in 2018 after she received her PhD from Cambridge and did a postdoc at UC Berkeley. Today, she's going to talk to us about her important work on developing energy storage solutions for the grid and electric vehicles, which we're very excited to learn more about. So, Raphaele, please.
Hi, can you hear me? And
yeah.
Can you see my screen?
We can also see your screen, yes.
Great, okay. Thank you for the kind introduction, Manoush. And thanks, Mark, Manoush, and Igor for inviting me to talk today. So as Manoush mentioned, I'm an assistant professor in the materials department, and my focus is working on rechargeable batteries. So it's a nice transition from the previous talk here. So today I'm going to talk about energy storage technologies for grid applications, but also for electric transportation. I'll put my laser pointer here. Okay, so I just want to start with the first energy storage facility that was built in the US in 1929. And this was the Rocky River Pump Storage Plant, where you have here this energy storage facility by the Housatonic River in Connecticut, where we are pumping water from the river and storing it in a reservoir 200 feet above the pump. And so I'm sure you are aware of this, but I'll just make sure everyone is on the same page here. Why are we storing energy using these types of storage plants? So this is showing you a graph where we are showing you the fluctuations in energy demand throughout the day and how this compares to the energy supply. So here we are assuming that we have a constant energy supply throughout the day, but our energy demand is low at night and it's high during the day. And therefore it makes sense to store energy, the surplus of energy that we are producing at night when there is low demand, and so that we can feed it back into the grid at times of high demand. So this is called load leveling. There is another incentive here, which is energy arbitrage, where we want to be storing energy when it's at a low cost so that we can resell it to the grid at a higher cost. And so this was done for the first time in the US using this pump storage facility, and there is an 8 square mile reservoir at the top here. And this reservoir is filled by pumping water from the river at periods of low demands and low cost. And the power generated by releasing the same water at a later time when there are higher demand rates and higher prices is lucrative, but it's also important for load leveling. So what's the current state of electrical energy storage in the US? So right now, the US has the infrastructure to generate about 1,100 gigawatts of electricity, but it can only store 23 gigawatt of energy, which means that it can only store 2.1% of the electric power that's being produced in the US. In comparison, Europe is at around 10%, and Japan is leading here with 15% of the electrical power that's delivered that is cycled through a storage facility. So worldwide, we have a number of energy storage projects operational at this time, around 1,300. 18 are under construction. 40% of them are in the US. And within the US, as you can see from this map, California is leading. So it has the largest number of energy storage projects, more than 200, so 215 here, which allows the storage of 4.2 gigawatts of energy. Besides load leveling and energy arbitrage, being able to store energy is important to prolong the lifetime of our energy infrastructure. And as was mentioned in the previous talk, our energy infrastructure is aging, and it's approaching, or it is even beyond its intended lifetime. So being able to prolong the lifetime of energy infrastructure is an important goal for energy storage. So if you look at this pie chart here, this shows you the type of energy storage facilities that are installed at this point in the US. As you can see, most of the electrical energy storage for the grid is in the form of electrochemical energy storage, followed by thermal storage, pumped hydro, and electromechanical. So just a few definitions here. Electrochemical By this, we mean batteries or supercapacitors that store energy as chemical energy or by charge separation. Compressed air is one type of electromechanical energy storage technology where you're compressing air under pressure in an underground cavern, and you store it in this way. Flywheels use kinetic energy, rotational energy, to store electricity. Pumped hydro is what we've just discussed. So here, electricity is used to pump water from a low reservoir to a high reservoir. And thermal is when you are producing an excess energy that is stored in the form of cold or heat. Most of the time, this is done with molten salts at high temperature. So we have a number of options here, which have very different characteristics in terms of their discharge time at rated power meaning the maximum power input that they can handle. And they also differ in the overall power rating of the technology. So supercapacitors, for instance, are good at storing at high power applications, so they can deliver power very quickly, they can deliver energy very quickly, but for a short amount of time. So they're not great for long-term energy storage. Batteries are, they have larger discharge times, they can store more energy. The power rating is not as high as supercapacitors. And if we get to compressed air energy storage, so CAES here, and pumped hydro, both of these have very large power ratings. So you're able to, and large discharge time. So you're able to store a lot of energy and you can release it over hours to days. So it does take time to release it. It's much more suitable for long-term energy storage. So overall, there's no technology that's perfectly suited for every energy storage application. When you want to think of the type of technology that's most suited for particular projects, you need to think about three sets of characteristics. One of them is energy and power. So if you're interested in smoothing the variable energy output, then this requires high power technologies. If you're interested in longer term energy storage solutions, you want to look at high storage capacity. Supercapacitors and flywheels are high power, so they're more suited for short-term storage solutions like frequency, control, etc. Batteries, compressed air, energy storage, pumped hydro are medium to long-term energy storage solutions. So they're slower at delivering power, but they will deliver for a much longer time. Reliability and durability is also a characteristic that's important to be aware of. Kinetic and thermal systems generally operate indefinitely if you have a small amount of maintenance routinely. However, electrochemical cells in batteries will degrade over time. So there is a need for replacing these batteries fairly regularly. And finally, cost efficiency and value generation is, of course, an important metric here. We talk about levelized cost of storage of various technologies. These types of analysis are making a number of simplifying assumptions. And so we really need to focus here on the particular project that we are dealing with to really assess what technology is best suited. For instance, we need to look at the performance requirements for this particular project, local policies, the efficiency that we need, even the available space that we have for this energy storage technology. So these are all the deployed energy storage technologies in the US at this point. Each of them have limitations, which I will go through now. So pumped hydro, for instance, is highly efficient, but it is limited geographically. We need these large reservoirs. This also raises environmental concerns and high capital cost for building these facilities. Flywheels are limited to power management. They're not great for longer term energy storage. Compressed air is fairly inefficient. So the conversion from compressed air energy to electricity is around 25 to 45%. So this is fairly inefficient, and it's also geographically limited. Thermal storage is plagued with inefficiency, but it is still profitable in concentrating solar power plants. So this is really the exclusive place where we use thermal storage, because these plants already have molten salts. And so it's easy for us to to store power as heat in these molten salts. Okay, but overall, lithium-ion batteries are dominating the energy storage market. That was mentioned in the previous talk. And this is a shift from prior to 2010. So prior to 2010, really the only option for grid storage was pumped hydro. And since 2013, lithium-ion batteries have really led the energy storage market. This is a good illustration of a battery plant here, a battery farm. And this is the largest battery farm in the world. And it's just been built in California. This is in San Diego. And as you can see, this is what I'm showing you here is from August 2020, where the last batteries have been installed. And this particular farm can store about 250 megawatts for an hour. So why has lithium-ion batteries, why have they dominated the market since 2013? They've benefited from large-scale applications outside of grid storage. So electric vehicles is one, portable electronics is another. And so these other applications have led to rapid price cutting for this technology. At this point, it costs around $350 per kilowatt hour for grid storage applications for lithium-ion batteries. And there is also an expectation of rapid growth in the deployment of electric vehicles, which will continue to help grid storage deployment of lithium-ion batteries indirectly. This expectation for rapid growth is fueled by government commitments to the transition to electric vehicles. Again, a really good example of this is coming from California, where by 2035, all passenger cars and trucks will need to be zero-emission vehicles. All new passenger cars. So these types of policies are really helping the deployment of electric vehicles. Okay. However, there are also some risks associated with having a dominant technology here. One of them is the technology lock-in effect, which says that a dominant design can drive out competing technologies that could perform the same function. And so here we really need to continue looking at alternatives to lithium-ion batteries, because there may be a time where performance improvements will plateau and cost reduction will plateau as well. In addition, there are some shortcomings of lithium-ion batteries. The main one that is also publicized a lot is the safety of these lithium-ion batteries. Durability is a concern to cycle life, charging time. Materials requirements may set a floor on cost reductions, and the uncertainty about material supply chains is also a concern. So this, I'm showing you here a plot where I've plotted here the natural abundance of different elements that are making up lithium-ion batteries, but also other types of batteries, and the price of these of the raw material. As you can see, the current technology is based on lithium, on cobalt here, nickel here. All of these three elements are both have a low abundance on Earth. Also, cobalt, for instance, is toxic, and it can only be mined in the Democratic Republic of Congo and Zambia. So supply chain uncertainty is high for these elements. So we're trying to look right now at alternative battery technologies. I'm certainly involved in that thrust here. Vanadium redox flow batteries are investigated at this point. Some redox flow batteries are already implemented for grid storage. But these types of redox flow batteries could be cost competitive with lithium-ion batteries soon. And one of the advantages of this technology is that these batteries can last far longer than lithium-ion batteries. I'm particularly involved in sodium-ion batteries. So there's a lot of research going on sodium, magnesium, and potassium-ion batteries, where the idea here is to replace lithium by another metal that can perform the same function, but is much more sustainable and lower cost. Hydrogen energy storage is also emerging. In this case, the core process behind hydrogen energy storage is electrolysis, where we are converting electricity into hydrogen energy by splitting water. So here we have a water molecule being split into hydrogen gas and oxygen gas. And we can then store hydrogen gas. Generally, it's stored either using physical methods like compressed gas, cryocompressed gas, or liquid hydrogen. or we're using materials. And in these materials are porous, and hydrogen can be stored in the cavities of these materials or at the surface. And so the idea here is that if we were to store hydrogen without compressing it or without a material to store it, there would be a very low energy per unit volume. And so here we're really trying to increase the energy density of hydrogen storage. Once we've stored it, we can then consume hydrogen in 3 different ways. One is as a fuel. So we would use fuel cells to reconvert hydrogen energy into electricity. And this can be used for backup power systems, fuel cell electric vehicles. We can also use hydrogen as feedstock to drive certain chemical reactions in refineries, such as hydrocracking, sulfur removal, or we can blend hydrogen produced in say, using renewable energies, and we blend it with natural gas. So we can feed it back into natural gas pipelines and can use it as a fuel. So I guess the question now is, what should we be doing moving forward? What is the best option between lithium-ion batteries and hydrogen fuel cells? Well, I don't necessarily have an answer here, but I'll give you a few points of comparison. So fuel cells depend on the supply of hydrogen, and the US is a major producer of hydrogen. It produces about 10 million metric tons of hydrogen every year, mainly through reforming of natural gas. Hydrogen has the highest energy per unit mass of any fuel. Current fuel cell electric vehicles will use hydrogen in liquid form, and they could achieve much longer ranges than typical electric vehicles based on batteries. However, the cost of manufacturing is very significant, and the cost of filling a tank with H2 gas is also very significant. So this is holding back this technology. In terms of grid storage applications, hydrogen energy storage is still too costly. The major issue here is the low volumetric energy density of hydrogen gas, which remains a significant challenge, especially for transportation. In terms of batteries, here we rely on the production of lithium. US is not a significant producer of lithium, so we have to import it, mainly from Chile and Argentina. Lithium-ion batteries are a relatively mature technology. I guess the high-end electric vehicles right now can store about 250 watt-hour per kilogram. A cost reduction of this technology has led to a cost of $150 per kilowatt hour for electric vehicle applications. It's a bit higher for grid storage, $350 per kilowatt hour. And the mile range of the most expensive electric vehicles is around 370. So it is becoming certainly competitive here. Overall, lithium-ion batteries they combine lightweight, high energy and power, near 100% efficiency, and low self-discharge. All of these characteristics are unmatched by other technologies. But this might be a bit of an overkill for grid storage applications. So this is very important for vehicle applications where you want a lightweight battery. However, for grid storage, we don't actually need this. And so I think there is still a lot to be done on the side of R&D to improve the sustainability and further reduce cost by moving beyond lithium-ion. Okay, so I'll finish quickly with showing you the trends so far in the last couple of years in terms of the deployment of energy storage technologies. As you can see from this chart, energy storage deployment has increased in the near past until 2018, and in 2019 you have a slight slowdown of energy storage deployment, which is due to unsupportive policies. And so really this highlights that the growth in these technologies depends heavily on policy intervention still. And we need to return to double-digit growth for several reasons. One of them is to keep on track with the International Energy Agency's Sustainable Development Scenario. And this particular scenario was created and outlines a major transformation of our global energy system to fulfill 2 goals. One is to hold the global temperature rise to 1.8 degrees Celsius in order to fulfill the Paris Agreement, the goal of the Paris Agreement. The other one is to deliver on 3 sustainable goals that have been set by the UN. First of them is to achieve universal access to energy. Second is to reduce the severe health impacts of air pollution. And the third one is to tackle climate change. However, in 2020, we've had also other types of challenges. The lockdown in many countries has led to significantly reduced electricity demand. And so you can see from this plot is showing you the reduction of electricity demand as a function of the number of days since the lockdown. And you can see that the decrease is significant, down to 30% in Italy. And this is because residential demand has gone up during the lockdown, but it's far outweighed by reductions in commercial and industrial operations. So the International Energy Agency estimates a 5% reduction in global electricity demand in 2020. This has also had an impact on energy storage technologies. The 2020 crisis has reduced battery production because this requires a complex supply chain, which was disrupted. But the major impact has been on hydrogen energy storage, which is still at the stage of demonstration. And in this case, we need a well-coordinated supply chain and significant capital, and neither of these were great in 2020. So to finish with an outlook, lithium-ion battery storage will continue to be most widely used for several years at least. And the future of energy storage is really dependent on the extent to which electric vehicle technology developments will spill over into grid storage batteries. Other storage technologies also experienced a resurgence in 2019. There have been 6 compressed air energy storage projects that have been announced in China. Gravity storage is gaining traction in the UK. Australia is creating new pumped hydro storage projects. But overall, storage remains strongly dependent on favorable and stable policy environments. It did underperform in 2019 for this exact reason, largely due to uncertainty and slow progress in establishing rules for the deployment of energy storage. So I'll finish there. I may have gone a bit over time, so I'll stop here.
Great. Thank you very much for the very nice overview talk, Raphael. I think it's very interesting. Several important facts were brought up, including the effect of the pandemic on research and electricity. Very interesting. I would like to ask questions from the audience. We have Jordan Finzel. I think you see his question, but I'm going to read it out loud. Which technologies are in use in Japan, where you know that 15% of all electric generation can be stored? Are these technologies geographic specific, example pumped hydro, or applicable generally throughout the world?
Yes, and I would say yes, pumped hydro is still, I will say something that's also interesting about pumped hydro is that even though there are a few large-scale energy storage pumped hydro facilities in the US, they actually store a lot of energy because they have these huge reservoirs of energy. So if you actually look at the energy that's stored, pumped hydro is still the major storage technology, which is also applicable to Japan. So they do have pumped hydro, and they certainly have a lot of battery electrochemical energy storage plants over there.
Great. Thanks for the question, Jordan. If there are any questions, please feel free to type them in once our next speaker, and I would like to ask our next speaker, Professor Mesic, to set up.
Okay, I'll stop.
Well, we have Ehsan Saidi asking, do you expect the same exponential growth for hydrogen as you see for lithium-ion batteries?
If there is, well, I think lithium-ion batteries, as I mentioned, really benefited from having these different applications that are very relevant to the general population, electric vehicles, portable electronics. This is not the case for hydrogen storage at this point. There are lots of applications of hydrogen energy storage, but there's not this incentive that we've had for the last 2 decades for lithium-ion batteries. So while there will be growth, I'm not sure it will be as exponential as for batteries, mainly because of this poor, low volumetric energy density of hydrogen. It's hard to move around with a tank of hydrogen gas.
Wonderful. Thank you so much, Raphael. I think you need to stop sharing. Yeah, perfect.
Hey, Manoush, this is Mark. I'd like to ask Raphael one more question.
Of course, yeah. Go ahead, Mark.
So lithium-ion, my understanding is has some recycling issues and things like that, right? Did the hydrogen technologies, I realize hydrogen's pretty volatile and all that, but the hydrogen technologies, are they sort of inherently better for society that way, or?
So it's certainly, it can be much cleaner. I also mentioned that lithium-ion battery has an recyclability issue because we're not looking into it. It's still not cost effective at this point. And there is it's a bit of a loop here where there's no R&D in there, not sufficient R&D, and therefore it's not viable yet. And that makes it difficult to find funding for this type of research. So I do think that lithium-ion batteries could be improving in the sense of recyclability, but there is just no real incentive right now to recycle lithium. It's still cheaper to mine more, which is a huge problem.
Thank you. By the way, that was a great talk. Thank you very much.
Thanks.
Yes, wonderful talk. Thank you so much, Raphael.